Hello student, welcome in our 11th lecture. In the previous lecture, we have seen the chromatographic theories. In that, we have discussed the plate theory and the red theory. In the red theory, we also discussed the Van Dimter equation. Different terms involved in this Van Dimter equation. That part we have already seen in the previous lecture. Now, in the today's lecture, we are going to discuss the RS term, RF value, and qualitative and quantitative application of this chromatographic methods. So, the content of the today's lecture is the first is the resolution term. It is denoted by letter RS. Second, retardation factor. It is denoted by term RF. And the qualitative and quantitative application of these chromatographic methods. This part we are going to discuss in the today's lecture. This lecture is the last point of this second chapter. So this part, it is the last point from this chapter. So we start with the first, that is resolution term. So resolution, it is denoted by letter RS. It means the separation. Separation of peak on chromatogram is the resolution. In the previous lecture, we discussed this chromatogram. What is chromatogram? Chromatogram, it is nothing but the graphical representation of detector response versus time and separation of the compound shown by that graph. That is nothing but the chromatogram. So here two chromatograms are there. In the first case, detector response versus time and two separate peaks are observed. While in the second case, here detector response versus time and we are getting this merge peak. Okay, so by observing these two graphs, we see that here the separation, it is completely done. While in this case, the compounds are merged. That's why the separation, it is not better. So here the separation of the two components on the chromatogram shows the good separation. While here the merge peak, it is not shows the good separation. Okay. Then resolution is the ability to separate two signals in chromatography. It's the ability to separate two peaks. So it is calculated by using this formula Tr2 minus Tr1 upon 1/2 W1 plus W2. So here one graph is given, chromatogram is given, detector response versus time. So here the two components are completely separated. They shows the two different peaks. That's why we say that these two components are completely separated. Here this is the solute A and this one is the solute B. So this part from this point to this, it is called the retention time for the solute 1, while this one is the retention time for the solute 2. Okay, and this Tm, it is the dead time, and the width, it is nothing but the width of this solute 1 and this one is the width of the solute 2. So here the terms are Tr1, it is the retention time for the first solute. Tr2, it is the retention time for the second solute. W1 is the width of the first solute. W2 is the width of the second solute. If the peaks are sufficiently close, W is nearly the same for both peaks and resolution may be expressed. Okay, if the W, it is sufficiently close, then the resolution may be expressed. Then we see the problem. Such a types of problem asked in the exam also. In 30 centimeter column, we are going to take two components A and B. They shows the retention time at 15 and 16. From the peak, the widths are 10 and 2. Then calculate the RS term. So the formula is RS is equal to TR1 minus TR2 minus TR1, that is nothing but the delta T, and below that summation of a W. So here this delta T, it is nothing but the 16 minus 15. 16, it is the retention time for the second solute, and this one is the retention time for the first solute. This one is width of the first solute and width of the second solute. So by solving this, we are getting 1 upon 12, and again by solving this, we get the 0.0833 answer, that is nothing but the resolution of the two components. Okay. So such a types of problems are asked in the exam also. Then we see one graphical representation. One chromatogram is there. Here the detector response versus time. In the first peak, we observe that the RS term, instead of RS we write here R. So it is the RS term. It is nothing but 0.50. So here there is no separation. Then here the RS term, it is 1. So we are getting the separation like this. And if the RS is 1.5, then we are getting a separate two peaks and the separation is observed. That means greater the distance, more is the resolution, or vice versa. More is the resolution, greater the distance in between the two peaks. Okay. So by observing this chromatogram, what we conclude that if the RS value it is greater than 1.5, then and then we observe the good separation, and if it is below the 1, then there is a no separation is observed. Okay. We see one more diagram here. In the first case, the RS is 1.1. Here the RS is 1.1. So poor separation is observed, thus low selectivity. In this case, the RS term it is 1.3. So we are getting partial separation, thus the best selectivity. While here the RS it is 2. That's why we are getting separate two peaks. They shows best selectivity. Okay. Then here the resolution of separation. The resolution of two peaks from one another, it is find out by this formula delta T upon summation W, or average width. Okay. So in the previous slide we also conclude that this resolution, if it is greater than 1.5, then and then we get the greater separation, greater resolution. So here also we see the different chromatograms. So here in the first case, here only 0.5 resolution is there. That's why there is no separation. Here 0.75. So here also there is a no separation. By drawing this tangent, we are conclude that these two components are different, but we are not getting a separate peak. That's why there is a no separation. Then if the resolution is 1, we are getting two separate peak. And at the last, if the resolution it is in between 1.5, then we shows the two separate peaks and they shows the better resolution. Okay. factors increasing the peak resolution. Due to which factor the peak resolution is increased, that are as follows. Increase the column length. As in the previous lecture, by increasing the number of theoretical plate, the separation of the component is the better. That part we already discussed in the previous lecture. That's why by increasing the column length, we can increase the peak resolution. Then second, decrease the column diameter. The diameter must be smaller. Then and then we get the good resolution. Decrease flow rate. Mobile phase, it is continuously flowing on the stationary phase. So if we decrease the flow rate, then we also get the good peak resolution. Okay. Then pack column uniformity. That means when we fill the stationary phase into the column, at that time the uniformity must be maintained. Then and then the separation, it is good. Use the uniform stationary phase, means packing material should be well placed in the column. Decrease the sample size. Then select the proper stationary phase, select the proper mobile phase, use the proper pressure, and use the gradient elution. This gradient elution, that means in the gradient elution two types of solvents are used. One is weak solvent and another one is a strong solvent. By increasing the ratio of that solvent, we are getting the good separation. So this gradient elution, it is most commonly used in this chromatographic technique. Due to that, we are getting the better resolution. Okay. So these are the factors increasing the peak resolution. Then the next term, that is the retardation factor. In short, we call it as RF value. Most of the time in the practical, we also find out this RF value. So it is very familiar to you. It is the distance. It defined as the distance traveled by solute divided by the distance traveled by solvent. So for that, we consider the figure here. This is a paper strip or the TLC plate. This is a baseline. On that baseline, we place a sample and we put this plate into the mobile phase. So what happened? Mobile phase, it is running over the stationary phase and the separation of the compound takes place. And the solvent, that means mobile phase, it is run up to this mark, that is called the solvent front. Okay. Then we calculate the value here. The distance from this baseline to solute, it is 2.1 centimeter. That is the distance traveled by solute. Okay. And this one is the distance traveled by solvent, that is 2.8 centimeter. Our formula is distance traveled by solute upon distance traveled by solvent. That's why putting the value 2.1 upon 2.8, we are getting 0.75. We know that this RF value, it is always less than 1. Then we get a better separation. If this RF value, it is 0, then the solute remains in the stationary phase and thus it is immobile. That means they are not moving on the stationary phase. It is immobile. Okay. If the RF value is 1, then the solute has no affinity for the stationary phase and it travels with the solvent front. If the RF value is 1, then what happens? If RF value is 1, this solute, it is move with the mobile phase and it is come up to this point. So there is no separation occur. Okay, if the RF value is 1. But if the RF value, it is less than 1, then we are getting the good separation, better separation. Okay. So in the exam, the questions are asked, calculate the RF value for the given compound. So you have to remember this formula. Then factor affecting on RF value. The first factor is the solvent system and its composition. Okay. Then temperature, the quality of the paper, and the quality and the nature of the solvent used. So these factors affecting on the RF value. It is very simple. So you have to remember this factor. Then the last point from this chapter, that is qualitative and quantitative analysis or qualitative and quantitative application of this chromatographic technique. So it is widely used to determine the purity of the substance. By the column chromatography, we are purify the organic compounds. It is commonly used for the separation of a molecule. For example, it is used to remove the pesticide and insecticide like DDT in the water. In pharmaceutical companies, it is used for producing the pure metals, for medicines, and also for checking the contamination present in the medicine. Also, in the pharmaceutical industry, to identify the drug, avoid the impurities, determine the stability, this technique is used. Along with that, heavy metal analysis, then pesticidal residue and microchemical analysis of drug, that is also done by using this technique. It is used in pharmacy for detecting the chiral compounds, means enantiomer, optical isomer, that are detected by using this chromatographic technique. In food industry, this technique is very useful for analyzing and separation of additives, proteins and amino acid. And also in many food industries, sweetener analysis in the fruit juice, that can also be determined by using this technique. Then preservative analysis is also determined by this chromatographic technique. Okay. It is used in forensic science, determination of steroid in the blood, urine and sweat. For that, this technique is used, and it is also used in identification and quantifying the aromatics and volatile substances of the medicinal plant. Where it is used, identification and quantifying the aromatics and volatile substances of the medicinal plant are also identified using this technique. Okay, so this is the last point of the second chapter. In the next lecture, we will discuss our third chapter, gas chromatography. Okay, thank you.